Hello, welcome to lecture in algorithm series. In this lecture, we will be discussing what is recursion tree, how can we use recursion tree for visualizing the flow of execution of recursive algorithms. So, let us quickly recap what is recursion. Recursion is a function or algorithm calling itself directly or indirectly. Whenever we write a recursive programs or recursive algorithms, there are two steps. The first one is the recursive step, the part where the algorithm calls itself with a modified input, and it should move towards the base case. The base case or a terminating case is the algorithm on trivial cases, trivial inputs. So take an example, factorial of n. So when n is equal to 0 or n equal to 1, factorial of n is 1. When n is greater than 1, that is a recursive case, that is n into factorial of n minus 1. So now what is recursion tree? Recursion tree is a graphical representation of the function calls made by a recursive algorithm. Here each node denotes a function call and each edge represents a call made from one function call to another. So this recursion tree is helpful in visualizing the flow of executions. It is helpful in tracing out the execution of the recursive algorithms, and it also helps in analyzing the time complexity. This is something that we will discuss in the next lecture. So let us consider an example. Or a typical recursion tree will be having like an initial call that will be at the root node, and whatever the subsequent calls, those will be a part of the internal nodes, and the base cases will be at the leaves. So consider an example for a factorial. Now let us consider a recursion tree for factorial of 4. So factorial of 4 factorial of 4 is at the root node, and factorial of 4 calls factorial of 3, and factorial of 3 calls factorial of 2, and factorial of 2 calls factorial of 1. So there are edges, and factorial of 1 is a base case, so that is the leaf node. And you can also find out the value of the factorial of 4 by tracing out the execution. Factorial of 1 returns 1, as a factorial of 2 is expected to return 2 into factorial of 1, so we'll get 2. And similarly factorial of 3 is expected to return 3 into factorial of 2, so we'll get 6. And factorial of 4 is expected to return 4 into factorial of 3, so we'll get 24. The final value of factorial of 4 will get 24. This is how we can trace the execution by using a recursion tree. So let us consider another example, that is finding a nth Fibonacci number. So where now this sequence is when it is the first number is 0 and second number is 1. All the subsequent numbers are sum of previous two numbers. So Fibonacci of n minus 1 plus Fibonacci of n minus 2. So let us draw a recursion tree for fourth Fibonacci number. With an argument 4, if we call the Fibonacci 4, so as n is greater than 2, so it calls two recursive functions, Fibonacci of 3 and Fibonacci of 2. So we have two nodes for Fibonacci of 4, and Fibonacci of 3. Fibonacci of 3 again n greater than 2, so we have two function calls, Fibonacci of 2 and Fibonacci of 1, and Fibonacci of 1, 2 are leaf nodes, and as you can see that Fibonacci of 2 returns 1 and Fibonacci of 1 returns 0, so we get 1 for Fibonacci of 3, and for Fibonacci of 4, 1 plus 1, 2. So fourth Fibonacci number is 2. This is how one can find out the value returned by Fibonacci of 4 by using recursion tree. So let us consider another example which was asked in GATE 2024. So we have a function called foo which takes 3 arguments x, y, q. When both are less than or equal to 0, the function returns q. Otherwise there are recursive calls, and only x is less than or equal to 0, it has a single function call. Similarly, y is less than or equal to 0, it has single function call. Otherwise it has 2 function calls. So in those function calls, either x is decremented by q or y is decremented by q. Now what is the value of foo, 15, 15, 10? So foo, 15, 10, 15, 15, 10 is the root node in the recursion tree, and you have as the values of x and y are greater than 0, so we have 2 function calls, and the first function call decrements y by q, so 15 minus 10, so we get 5. So now this is a function called foo, 15, 5, 10, and another function call is decrease x by q, so we get 15 minus 10, 5, so 5, 10, 15. And again we have a case where x and y are greater than 0, so again we have 2 function calls, foo. So y is decremented by q, so 5 minus 10 we get minus 5. So similarly x is decremented by q, so we get y, 5, 5, 10. Okay, so and when you continue this, when you continue this, you are going to get something like this. As y is less than or equal to 0, so only x will be decremented until it will become less than or equal to 0, and then from there it returns a q. So q is 10 always, so 10 will be returned here, and when both are greater than, for the other one, foo, 5, 5, 10, when both are greater than 0, so again it is having 2 function calls, 5 minus 5, 10, minus 5, 5, 10. So both will return 10, so you will get a value 10 plus 10, 20, and for this you will get a value 10 plus 20, 30. And similarly here we have this 5, 5, 10, you will get 20, so 20 plus 10, 30, and 30 plus 30, 60. So this is how one can calculate the foo, 15, 15, 10 value by using recursion tree. Okay, and so there is a homework problem which was asked in GATE 2025. Now you have to draw a recursion tree for the following function called foo a comma 9. That means array with 9 numbers are considered, and each time that array size is decreased by 1, and it will point to the next element of the array. So when first element as well as the second element both are same, you have 1 plus increment that 1, you have 1 plus a recursive call, otherwise direct recursive call. When the base cases are when the size is 0 or size is 1, return 1 and return 0. Okay, now draw the recursion tree and find the foo a comma 9 value. So now the recursion tree can be used to trace the output, as we have seen here. We can propagate upwards those results, whatever the intermediate nodes or the base case nodes results, which can be propagated upwards to find a result returned by the root node. Okay, and this is also an excellent for debugging and verifying whether the recursive logic is working or not. In the next class, we will see how to use the recursion tree for finding a time complexities.